Hey guys, we are at the last video for the Spring 2020 COVID-19 dismissal for this class. Congratulations on making it to the final full assignment. I really appreciate all your hard work getting up to this point. I hope you've learned some stuff about chemistry. It hasn't been too boring, but I know it's been tough given the circumstances. Anyway, we're going to do one last skill, and a very important skill to chemists that you'll see a lot more in chemistry, and that is balancing chemical equations. So some learning objectives for you. First, I can describe the law of conservation of matter and its importance to chemical equations. And then second, I can balance chemical equations. So that's the skill we're going to practice today. It's one of my favorite little games, balancing. Before we jump into it, I do want to just note that we've really only scratched the surface of chemistry in studying synthesis and single replacement reactions and ionic compounds. There's still the whole world of covalent compounds and many other types of reactions. So I just wanted to say we've studied synthesis and single replacement reactions as they apply to ionic compounds, but many other classes of chemical reactions exist, including decomposition, double replacement, acid-base neutralization, combustion, reduction oxidation, and equilibrium. We don't have time to study these or many of the other skills in chemistry, but you're going to go much deeper with what you've learned and into new territory when you do take chemistry. After doing this distance learning intro to chem, I would highly recommend that all of you have gone through this. Sign up and do chemistry next year. I hope because of this, it will be much easier to kind of jump into that discipline that many refer to as a pretty hard class. So I also bring up those different types of chemical reactions because I'm going to be talking a little bit about combustion reactions today as I kind of bring us through the process of balancing chemical equations. So first, let's jump into the law of conservation of matter. In any chemical reaction, matter, and therefore mass, is not created or destroyed. It only changes form. And this is known as the law of conservation of matter, or the law of conservation of mass. In other words, the total mass of the reactants in a chemical reaction always equals the total mass of the products that come out of it. All the atoms that go into the reaction must also come out of the reaction. And we'll see why that's important in just a little bit. But first, just a question to get us started. If I burn 5,000 grams of wood and am left with 4,000 grams of ash, doesn't this violate the law of conservation of matter? Pause the video and think about that if you'd like, but I'll jump into my response. No, it does not violate it because there are other products coming out of that reaction than the ash, including the carbon dioxide and water vapor and smoke, that we're not accounting for. Also, there's another reactant, oxygen, in that combustion reaction that we didn't weigh. So we don't know how much weight in oxygen we burnt. We don't know how much weight in gases we produced. We just know that the solids going in were 5,000 grams of wood and the solids going out were 4,000 grams of wood. There are other products much harder to measure, namely gases. So let's talk about a combustion reaction. Let's talk about the combustion of propane on a barbecue grill. Propane, C3H8 gas, reacts with oxygen, O2 gas, to create carbon dioxide, CO2 gas, and water, H2O vapor. What is the chemical equation for this reaction? Hopefully at this point you could read through that sentence and write that out into a chemical equation. If you pause the video and try that, in a minute, you can restart it and hopefully you came up with something like this. Again, propane, C3H8, plus oxygen, O2, yields carbon dioxide, CO2, plus water, H2O. So that is a combustion reaction right there, specifically the combustion of propane. Just to simplify things again, make it the least busy as possible, I'm going to get rid of all those phases. This is a totally gaseous reaction. Everything that goes in and comes out is a gas. Let's just disregard those and look at the chemicals themselves. So here is my question to you. Does this chemical equation support the law of conservation of matter as it is written now. In other words, do all the atoms of each element that go into the reaction also come out? And I would ask you to look at that equation and try to come up with an answer to that question. Does what go in also come out? Let's see. So to do this, for me to answer that question, I would start by tallying up the atoms of elements on each side of the reaction, trying to get a count of what is going in and get a count of what is going out. And I would make a table like this. And when you go to balanced chemical reactions, your starting point will pretty much always be making a table like this. In this particular reaction, I list the elements carbon, hydrogen, and oxygen because those are my 3 elements present in this reaction. And now I'm going to go through and I'm going to write down the total number of atoms of each element on each side of the arrow, on each side of the yield sign. And again, you could pause the video and try this right now. But if you do this, you'll see that on the reactant side, I have 3 carbon atoms in that propane molecule. I have 8 hydrogen atoms in that propane molecule, and I have 2 oxygen atoms in that oxygen molecule. I'm just counting the subscripts here. On the product side, I have 1 carbon atom because there is no subscript, so it's assumed to be 1. I have 2 hydrogens in the water, and I have 3 oxygens in total. Hopefully you can see where I got the number 3 from. There's 2 in carbon dioxide, and there's 1 in oxygen. So when I add them up, I've got 3 oxygens. And so now I've got to ask myself, is it balanced? And it's not. And I know that because as this reaction proceeds, 2 carbon atoms are seemingly destroyed. 3 went in, but only 1 comes out. 6 hydrogen atoms are destroyed. 8 go in, but 2 come out. And then somehow 1 oxygen atom is created. 2 go in, but 3 come out. So this does not jive with the law of conservation of matter as we have it written. And so we need to develop this skill called balancing chemical equations to figure out how to make this jive. So let's get into it. We must balance this equation by making the number of atoms of each element on the reactant side equal to the number of atoms of each element on the product side. But in doing this, and this whole slide is actually to tell you what you can't ever do. You can never change subscripts or you change the chemistry altogether. I'll show you what I mean by that. You might have looked at that equation and said, well, if I just make O2, O3 instead, and if I just make CO2, C3O2 instead, and if I just make H2O, H8O, then when I tally it up, it's all balanced. What goes in does come out. But when I do that, I've now changed the compounds I'm talking about. O3 is ozone, it's not oxygen gas, and so ozone is not actually a reactant in the combustion of propane. And then these things on the product side just don't even exist. There is no molecule H8O, and it's certainly not water. Same with C3O2, that's not carbon dioxide. So do know that you can never change subscripts when it comes to balancing chemical equations. Do not do that. Changes the chemicals altogether. So what can you do, you might ask? We can, however, add whole numbers, which chemists call coefficients, in front of each substance, elements, or compounds to change the number of molecules going into and out of the reaction. And so in any chemical equation, when you go to balance it, there's a certain number of places you can make moves. It's in front of every new substance. Here I have 4 substances: propane, oxygen, carbon dioxide, and water. And so I put blue lines in front of each of those substances so I know where I can make my moves in this game of balancing. And again, I would make this T-table, this table to tally up for each element. How many atoms do I have on the reactant side? How many atoms do I have on the product side? And then I use this table to guide me through the problem. When every element has its reactant side equal its product side, that's when I know I'm done. And so here you can see we've already filled this table in before to prove that it wasn't balanced. So I've just replaced those numbers. And that is my starting table. So what am I going to do? First, personally, what I would do in this problem is, let me back up a little bit. I would look at this and I'd say, okay, carbon is the first thing in my list. I have 3 on the reactant side, but only 1 on the product side. And I'm asking myself, what number can I add and where to get myself to 3 carbons on the product side? And so looking on the product side, the only place that carbon exists is in CO2. And so in front of CO2, I would add a 3, and that 3 is indicating 3 molecules of carbon dioxide. So I would add a 3 in front of CO2 to represent 3 molecules of CO2. When I have 3 molecules of CO2, that means I have 3 carbon atoms on the product side. And that's because number of atoms equals coefficient times subscript. So the invisible subscript on carbon is 1. 3 times 1 is 3. So I have 3 carbon atoms on the product side. But then I also need to recognize what it's done to my oxygen. If I have 3 CO2 molecules, each has 2 oxygens, so in total, that is 6 atoms of oxygen. When I add the 1 atom of oxygen from the water, I'm now at 7 total oxygens. And so at this point, I've made a move, and what I would do is update my table. I chose to put a 3 there to balance carbon, but then I recognize that in balancing carbon, I've also changed oxygen. That 3 applies to each element in the compound. So again, 3 times 2 is 6, plus the 1 from water gets me to a total of 7 oxygens on the product side. So let's move on. What would I do next? Before I show you, my thought process here is I'm looking at the next thing, which is hydrogen. I have 8 on the left, only 2 on the right. So I'm asking myself, what number can I put here in front of water so that when multiplied by 2, it'll get me up to the 8 hydrogens I need. So here, of course, I would say next, I'm going to add a 4 because 4 times 2 equals 8 in front of water to represent 4 molecules of water. This means I would have 8 hydrogen atoms on the product side in total. Again, 4 times 2 is 8 hydrogen, but because oxygen is also in water, I have to ask myself, what does that do to my total count of oxygen? When I go to add up oxygen, I have 3 times 2 on the carbon dioxide, so that's 6 total oxygen there, plus 4 times 1 in the water is 4 more. In total, when I go to update my table, yes, I've balanced hydrogen at 8, 4 times 2, but I've also increased oxygen up to 10 now. Again, 3 times 2 is 6, plus 4 times 1 is a total of 10. So I'm getting there. I balanced 2 rows, carbon and hydrogen, but now I need to balance oxygen. And so looking at my table again, I would say I'm now short oxygen on the reactant side, and I'm asking myself, what number can I add right here in front of the oxygen that when multiplied by 2 will get me up to the needed 10 oxygen atoms? And let's see. Finally, I would add a 5 in front of O2 to represent 5 molecules of oxygen. This means I would have 10 oxygen atoms on the reactant side, and everything is now equal. So again, I have 5 there. 5 times 2 is 10 total oxygen atoms. And so my carbon's balanced, my hydrogen's balanced, and my oxygen's balanced. I would call this problem done. When no coefficient is written in front of a compound, like the C3H8, you can assume the number is 1. You could write it in, or you could just leave it blank. Everyone knows to assume it is 1. And again, the table tells me that I'm done. And so every row is equal. I am done balancing. Here's a quick kind of visual representation of what we just did. We added numbers of molecules to the left and right side of that equation so that if I look for each element, I have an equal amount on either side. Carbon here is represented in black. The 3 black spheres in propane equal the 3 black spheres in the 3 molecules of carbon dioxide. Hydrogen is represented in white. 1, 2, 3, 4, 5, 6, 7, 8 molecules of or atoms of hydrogen in propane equal the 8 atoms of hydrogen and water. And then lastly, I've got 5 diatomic oxygen molecules over here. So 2, 4, 6, 8, 10 total red oxygen atoms. And when I count them over here, 3, 6, 7, 8, 9, 10, I have 10 red spheres as well. So that's just kind of a pictorial representation of what we just did to balance this equation. And of course, now we have a chemical reaction that does abide by the law of conservation of matter, of mass, and it is perfectly balanced as all chemical reactions should be. We've not been writing them this way so far. So here are just some helpful tips, and then I'll do a couple examples, and then you'll give it a shot. First tip is the only place you can add coefficients is in front of substances, compounds or elements. So I like drawing a little line, like I did the blue line, in front of all my substances, my compounds and elements, so that I know where I can add numbers when I play this game. Definitely create a table to count the atoms of each element on both the reactants and product side. This lets you know when you're done. Update the table every time you add a coefficient. So you make a move by adding a number to one of those lines you just drew in, and then when you make a move, you update your table. And hopefully, as you practice this more and more, you'll start making more and more strategic moves that get you towards solving the problem. You cannot ever change the subscripts in a compound, in compounds. I can't stress that enough. When you do that, you're changing the molecule altogether, the chemical altogether, and you've just created something that doesn't exist. And know that balancing one element may unbalance others. Like we saw in the propane example, whenever we balanced carbon and hydrogen, it also changed oxygen. And so when you update a coefficient, it's got to apply to every element within that compound. Try to manipulate coefficients of lone elements last. Notice in the last one how we saved O2 for the end, because I knew that manipulating carbon and hydrogen was also going to mess up oxygen. So let's let oxygen get as messed up as possible and then just fix it in the end. And then here's a pro tip. If you're comfortable with this, if the same polyatomic ion appears on both sides of the reaction, you can treat that polyatomic ion as a single row in your tally table. And I'll show you what I mean by that in a little bit in an example. And then lastly, keep in mind that diatomic elements come in pairs. If you need to get to an odd number of that particular element, and all you have to work with is a diatomic element, a pair, then add a coefficient. By adding a coefficient to the diatomic element, first you should multiply all your coefficients by 2. I could do an example of that if people are confused. If not, don't worry so much about that. That might only come up in like PD level questions. All right, so let me do a couple more examples. Here's an example of the synthesis reaction of magnesium oxide. I've got Mg plus O2, O2 because oxygen's diatomic, yields MgO. And I know it's MgO with no subscripts because magnesium has a +2 charge and oxygen has a -2 charge. So they bond at a 1-to-1 ratio. So to start off, I'm going to make that table. I list my elements on the left, magnesium and oxygen. And then I'm counting how many I have on each side of the equation. On the reactants, I have 1 magnesium. On the products, I also have 1 magnesium. So far it seems like it's going to be balanced. But on the reactants, I have 2 oxygen. And on the products, I have only 1 oxygen. So you can't subtract anything off because that would require changing subscripts. So I'd ask you to think here, what move could I make and where to get me closer to having this problem solved? Think about it. Let's see what you came up with. Here's the move I would do. I would put a 2 in front of magnesium oxide. Why? Because that 2 will balance my oxygen. When I put a 2 there, the 2 times 1 gives me a total of 2 oxygen on the product side to balance the 2 oxygen on the reactant side. But in doing so, I also recognize that I unbalanced magnesium because when I put the 2 there, now I have 2 magnesium atoms on the right, but only 1 on the left. So I still need to make another move. And I would ask yourself, okay, what move should I make now to try to balance magnesium by increasing the left side? Hopefully you thought about it. Hopefully you came up with this. If I add a 2 in front of that lone magnesium atom out on the reactant side, then I now have a table that looks like this. 2 magnesium on the reactants, 2 magnesium on the products, 2 oxygen on the reactants, 2 oxygen on the products, and that right there is the solution to this particular problem. So I'd say that one was pretty easy compared to the first example we did. Let's do one more. And in this particular problem, we have a single replacement reaction, the single replacement reaction of potassium and calcium phosphate. And I intentionally wanted to do one with a polyatomic ion in it to show you what I mean about counting the polyatomic ion as a whole. So I'm treating PO4 as a single packet, and I'm counting it as a single packet. So when I do my tally here, I've got 1 potassium on the left, I've got 3 potassium on the right, I've got 3 calcium on the left, but only 1 calcium on the right. And then over here, when it comes to counting PO4, counting phosphate, I'm asking how many PO4s do I have? The 2 outside of the parentheses says I have 2 PO4s. And so I'm counting PO4 as a packet, and I'm saying I have 2 of them on the left. Over here, on the right, notice how it's not in parentheses at all. That's because I have only 1 PO4 in that compound. So that's why I put the 1 there. So maybe pause the video, maybe not, I don't know. Look at this and ask yourself, what move should I make to try to get this closer to being balanced? And here's one recommendation I would make for you. Notice how potassium shows up all by itself over here as an element. Calcium shows up all by itself over here as a reactant or as a product. So I know I can add to that spot right there and that spot right there without affecting any other element. So my recommendation would be to try to balance phosphate first. Try to ask yourself, what number do I need to put in where so that I can balance phosphate? And when it comes down to it, I hope you said put a 2 in front of potassium phosphate. If I have 2 K3PO4s, then in total, I have 2 PO4s. That also affects my potassium because 2 times 3 means I have 6. And so now I'm asking myself, well, what move will I make next? And I think there's 2 legit moves here to kind of finish up this problem. Hopefully one of the ones you said would be put a 3 in front of calcium. That would give me a total of 3 calciums on the product to balance my 3 calciums on the reactants. And now I'm so close. I have 1 potassium on the reactants, but 6 on the products. So what number do I need to put in where to balance the potassium? Hopefully you said put a 6 in front of the potassium. And that 6 times 1 would give me 6K on the left to equal the 6K on the right. And this problem is also complete. This is probably the most difficult skill we've practiced so far. So it's very important that you watch the video closely. Hopefully, I should have said that in the beginning, not at the end. Ask questions as you need them and seek out help as you need it. I will say on the assignment, the P level questions are pretty easy. They'll be kind of like that magnesium oxide reaction that we did just before this one. So those are on the easier side. The PD get pretty challenging. And so if you get stuck, please reach out, let me know. I'm here to help you. And then this is our last formal assignment of this course. I will have one more assignment for anyone who's in a PD standing and wants to get PD in the course. It's kind of like a take-home test that you can do over the course of next week. And if you have questions on that, please reach out as well. But I want to stress that if you're just looking to get the pass, you don't need to do that final assignment. Other than that, let me know what's up, and I hope you're all well, and I'll see you when I see you. Bye.